Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to continue our discussion of backpropagation and talk about how to find the gradient of our objective with respect to the input weights W and B. Let's recap our neural network equations again, along with our objective. First, we have Z, which is sigma of W transpose X plus B. Then we have Y, which is the softmax of V transpose Z plus C. Then we have our categorical cross-entropy objective. As before, it's convenient to have a variable to represent the activations at each layer, which is the value before we apply the activation function. Let's use A for the output, just like we did before, and let's use alpha for the hidden layer. So now our equations become alpha equals W transpose X plus B, Z equals sigma of alpha, A is V transpose Z plus C, Y is the softmax of A, and J is the cross entropy as usual. What makes this more difficult is that we now have many layers of functions. In other words, we have a function of a function of a function of a function with what looks like 5 levels. However, this shouldn't stop us from continuing, and we should just write down all the steps like we would normally do. So we want to find the gradient of J with respect to W and B. Luckily, each of these 5 derivatives are just the derivatives of the simple functions we looked at. So there's not much difficulty in the mechanical work that we have to do to take the derivatives. What is difficult about this is the conceptual part. In particular, we have to apply what is called the law of total derivatives. So as we've written them down now, these derivatives are wrong. So what's the problem? If you recall, there's this part where we transition from k prime to k. But remember what I said about dummy variables. They exist inside the summation, but not outside. The problem with this is, what happens to k? K appears on the inside, but it doesn't appear on the outside anymore. If you recall, k appeared on the outside for the weights V and C, because those were actually indexed by k. But now we have a k on the right-hand side and no k on the left-hand side. To answer this question, we have to take a little detour and talk about the law of total derivatives. The law of total derivatives is like this. Suppose we know the position of an object in a three-dimensional space with respect to time. So we have x of t, y of t, and z of t, which are some arbitrary functions. By the way, these variables, x, y, z, and t, for the purpose of this slide, have nothing to do with neural networks. You can think of them as the position of a planet moving in space. Now, suppose we have some function of the position called f. The question is, what is the derivative of f with respect to time? We know that f is a function of x, y, and z, which are all in turn functions of the time t. So we know that the chain rule will apply somehow. But the answer is somewhat non-intuitive. We have to multiply the partial derivatives of f with respect to x, y, and z with the derivatives of x, y, and z with respect to the time t. Then we add them together. We can generalize this formula so that we can have any number of variables which are parameterized by t. In this case, we just sum over each of the individual terms. So how does this apply to our neural network? Well, we have our objective J. J is a function of a and k for all n's and all k's. A and k is a function of WDM. Why is that? Well, it's helpful to draw a picture of a neural network. You can see that WDM is the weight that carries one input node to one hidden node. But remember that this one hidden node influences all of the output nodes. In other words, all of the big K outputs. You can even draw it out in a picture to see the analogy between the general form of the law of total derivatives and our specific form, which applies to a neural network. On the right of these diagrams, we have the function we want to differentiate, f in the general case and j in our case. In the middle, we have all of the intermediate variables, x of k in the general case and a of nk in our case. At the input, we have the parameter, t in the general case and wdm in our case. So what does this mean for us? It means that in order to get rid of this pesky dummy variable k, we actually have to sum over all the possible values of k. So notice that we now have a double summation over the output nodes, one over k prime and another over k. Lucky for us, we've already solved the inner part of these summations, so the innermost summation goes away. We know that these combine to just give us t minus y. By the way, since we know that the derivative for the weight matrix and bias vector are very similar, we'll just focus on the weight matrix for now and ignore the bias term until the end. At this point, we have 3 derivatives to solve. Luckily, these are not very difficult since we've done them all before, well, for the most part. The derivatives of the activations are simple because they are just linear terms. So the derivative of ank with respect to znm is just vmk, and the derivative of alpha nm with respect to wdm is just xnd. The derivative of sigma will be different depending on what sigma represents, whether you use the sigmoid, the tanh, or the rel-u. Luckily, we've already found the derivative of the sigmoid when we studied logistic regression, so it's not necessary to do it from scratch again. Of course, if you don't remember how it's done, you may want to do it by hand. For the other derivatives, you're encouraged to solve them on your own if you don't know how they're derived. It's basically just Calculus 1 homework. As mentioned earlier, for the purpose of these lectures, we're going to assume that the hidden activation is a sigmoid, but you can easily plug in the other derivatives for the other activation functions. Finally, we can plug in all the derivatives we just found to arrive at our final answer. As before, for the bias term, we just replace x with 1. The next step is to vectorize these gradients for our implementation, which is not as easy as it was for the previous lectures. This is because it involves quite a few more terms, but it also involves some element-wise multiplication, which is not the same as proper matrix multiplication. We can reason about how it works if we look at the shapes of each matrix involved. First, note that the z terms are just element-wise multiplication. So every time we have znm, we have 1 minus znm, so the indices are the same. There's no mixture of indices for z. So this term just turns into z times 1 minus z, where z is the full n by m matrix of hidden layer values. Also note that the circle with a dot in it means element-wise multiplication. For convenience, we can just call this z prime for short. It helps to consider the shape of each object we have to multiply. The first, t minus y, is of shape n by k. The weight matrix V is of size m by k. The z prime term, which we just vectorized, is of size n by m. Finally, x is of shape n by d. So you can see that this is not just a straightforward matrix multiply, because none of the inner dimensions match. But here's what we can do. First, let's take the first 2 terms, t minus y and v. If we transpose v, then we get k as the inner dimension, and this is a valid matrix multiply. The result is a matrix of size n by m. And by the way, it makes sense to collapse and sum over k, because we know that in the scalar form, we are summing over k. Luckily, this matches the shape of z prime, which is also of size n by m, so we can do another element-wise matrix multiply. Lastly, we have a matrix which is of size n by m, and x which is of size n by d. We want the result to be d by m, and we know that we have to sum over n, which is exactly what matrix multiplication does. So if n is the inner dimension, that means we'll sum over it. So in fact, what we want to do here is transpose x and do a matrix multiply with the matrix we found previously. By the way, if you prefer, we can write this more generically using z prime, so that it can be the derivative of whichever hidden activation function you choose. Similarly, we can do the same thing for the bias term, but remember that there isn't really a linear algebra symbol to denote the summation over an index, so we'll just write this out in NumPy form. Again, it's just the same term we had before, except without the x, or equivalently, what we would have if x was just 1.